Test 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. La 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 la. Hi and welcome to this new video. Hi and welcome to this new video in our lecture series on computational finance. Hi and welcome to this new video. Hi and welcome to this new video. Hi and welcome to this latest video in our lecture series on computational finance. Hi and welcome to this latest video. Hi and welcome. Hi and welcome to this latest edition. Hi and welcome to this latest video in our lecture series on. Okay, Pause und dann geht's los. Hi and welcome to this latest video in our lecture series on computational finance. I'm Gregor Weiss, I'm a professor of sustainable banking here at Leipzig University, and I welcome you to this latest video in computational finance, in which I will now present some findings on possible return risk profiles and the minimum variance portfolio in the classic theory on portfolios by Markowitz. In the last video, we've seen that in portfolio theory, we concentrate on the expected return as a desirable thing and standard deviation of returns or volatility as something that is undesirable, as a metric for risk. And now in this video, we want to look at the possible risk return profiles we can actually achieve in the two security case. So we have two securities, for example, two stocks, and we are combining them to get a portfolio. And in this two security case of the portfolio theory by Markowitz, the set of all possible risk return profiles is given by the set M that includes all portfolios characterized by a portfolio expected return and a portfolio volatility that both are given by these two equations. So the expected return, the expected value of the portfolio return, is the linear combination of the expected values of the return on stock 1 and 2, and they are linearly, actually convexly combined by the portfolio weight X. We mentioned in the last video that in the two security case, we only have one weight because we exclude short selling, borrowing and lending. So in this case, it's quite simple that if we put 30% in stock 1, then 70% have to go into stock 2. So the expected value is quite simple. For the standard deviation or variance of the portfolio return, it's a little bit more tricky, but actually this is also the standard formula for the standard deviation or variance of a linear combination of two random variables. So we have the weight X, you square it, multiply it with the variance of stock 1, then you you add the squared value of the counterweight, 1 minus X, times the second variance, and then you have to add 2 times X times 1 minus X times the covariance, or you can write it using the standard deviations and the correlation factor rho. Now next, we look at the space M of possible portfolios for selected correlation constellations, so for selected correlation coefficients. We start with rho equal to 1, that is perfect positive linear correlation. In this case, we get that the volatility of the portfolio return is simply given by sigma 2 plus sigma 1 minus sigma 2 times X, and the expected return on the portfolio is given by this second equation. If we now put it in a plot, we can actually see that on the next slide, the set of all these possible portfolios that we can achieve, given that the correlation is 1, is actually a straight line. We will see these types of plots on and on again throughout the next videos. These are plots where we have the standard deviation or risk on the x-axis, and we have the expected return on the y-axis. So the farther north or the farther up we go, we get a higher expected return for the same risk, and the farther we go to the right on the same horizontal line, that is, we have the same expected return but higher risk. So we want to go up and we want to go left. That's what we desire. And if we include two stocks, sorry, that's still in German, Aktie 1 and Aktie 2, that's German for stock 1 and stock 2. If we have two stocks and we insert the expected returns and volatilities of these stocks here, then for a positive perfect correlation of 1, the space of all potential portfolios between the two, they are given by the straight line between the two. So that's the case of perfect positive correlation. Now, as a second special case, we want to look at rho equal to 0. These are two uncorrelated securities. And for the portfolio volatility, we get that the portfolio variance or volatility is given by sigma 1 squared plus sigma 2 squared times the squared weight minus 2x sigma 2 squared plus sigma 2 squared. So we can also calculate the space of all possible portfolios if rho is equal to 0. And I'll come back to that later. Now next, we want to calculate the so-called minimum variance portfolio, or in short, just the MVP. How do we do this? Well, very simply, we take the equation, the general equation for the portfolio variance, and we minimize this. For this is high school math, we have to calculate the first derivative and equate the first derivative of the portfolio variance with respect to x to 0, and we are looking for the portfolio weight that minimizes the portfolio variance. If we solve for x, we get x star equal to sigma 2 squared divided by sigma 1 squared plus sigma 2 squared. And please note that if we have a weight that is between 0 and 1, this has to hold for two stochastic returns, because otherwise we would get an equation where we have to divide by 0, and this is not feasible. Next, we get the exact value of the minimum portfolio variance by plugging x star into the equation for the portfolio variance. And this gives us the actual variance of the minimum variance portfolio. It doesn't necessarily have to be 0. It can be non-zero, but we can calculate it if we are given the volatilities or variances of the two constituent stocks and securities. So this is sigma 1 squared times sigma 2 squared divided by sigma 1 squared plus sigma 2 squared. If you take the square root, we get the volatility of the MVP, and this is given by sigma 1 times sigma 2 divided by the square root of sigma 1 squared plus sigma 2 squared, and this has to be smaller than sigma 1 squared times sigma 2 squared divided by just the square root of sigma 2 squared, and thus we can see this is equal to sigma 1, and we can do the same solving for sigma 2, meaning that even though in spite of a correlation of 0, we might have a correlation effect, and the variance or volatility of the MVP is always smaller than the volatility of the two constituent stocks. So this is quite interesting to see that we have this effect here regardless of what the volatilities of stock 1 and stock 2 look like. Next, for the special case rho equal to 0, we calculate the sample space M, that is, it's a function expression for the expected value of the portfolio return given or depending on the portfolio volatility. In other words, we want to plot this in our sigma mu plots we've seen before, and we want to show how this actually looks like graphically. We have the portfolio expected return is given by mu2 plus mu1 minus mu2 times x. If we solve for x, this gives us the portfolio expected return minus mu2 divided by mu1 minus mu2. Thus, with x star, in the case of the minimum variance portfolio, the previous equation is the general case. If we plug in x star, so if we are looking at the minimum variance portfolio, this gives us this formula mu MVP for the expected return of the minimum variance portfolio. We know what the portfolio variance looks like, and we can now solve and equate these two equations. And if we reorder this slightly, we get the last equation. This is just some simple algebra. And finally, we can solve for x, and plugging this all into the equation for mu pf here. Again, this is just very simple algebra, but what we get in the end is a solution for the expected return of the portfolio in case we are looking at the minimum variance portfolio. And what we get is, in the end, the sample space in case M is uncorrelated. For the special case for rho equal to 0, the graph of the sample space M is the right arm of a hyperbole, with mu and sigma values of both individual securities as the endpoint. We've already seen this, that for security 1 and 2, in case of perfect positive correlation, we have those two stocks or securities as endpoints, and the graph is actually a straight line. Now, in case of rho equal to 0, we get the right arm of a hyperbole, so it's tilted to the left a little bit. The peak of the hyperbole arm describes the minimum variance portfolio because it's the point that is farthest left. And thus, of all the possible cases and all the possible portfolios, it is the one that has the smallest x value on the plot, and the x-axis gives us the variance or volatility, so it has to be the minimum variance portfolio. If this restriction that the portfolio weight is between 0 and 1, if this is neglected, we can also build more portfolios and more combinations. And we'll see this later on. So here on this plot, you can see how the straight line, in case of the perfect positive correlation, is now tilted to the left, and the point that is farthest left on the hyperbole arm, this is the minimum variance portfolio in case the two stocks are uncorrelated. Again, this is rho equal to 0. If we have a different rho, then of course we also get a different plot and a different minimum variance portfolio. What happens if we have perfectly negatively correlated securities? We do the same, all the calculations for mu and sigma of the portfolio. Now we plug in rho equal to -1, and we get the two equations for the portfolio variance. And we can also look at the minimum variance portfolio. Actually, in this case, the minimum variance portfolio can give us a portfolio volatility that is equal to 0. So portfolio risk can be completely diversified, and it then looks like this. We have the two securities, 1 and 2, as endpoints, and we started out as a straight line between the 2 points. It was tilted to the left to the form of a hyperbole, and now we have sort of what is 2 arms of a triangle, and the minimum variance portfolio is now on the y-axis, and that is the variance, volatility of the minimum variance portfolio is 0. So this is the case of perfectly negatively correlated stocks in the 2 security case. And in the next on the next slide, we can see we deal with the case of non-perfectly correlated securities, so where we have a rho between 1 and -1. And as you can imagine, if we started out as a straight line between securities 1 and 2, and we ended up as with a hyperbole, and then it was tilted even further to a triangle. Obviously, in case of a correlation between 1 and -1, we have a hyperbole that is somewhere in between these two areas. So in case we have rho between 1 and -1, we also can calculate the minimum variance portfolio, and it's somewhere between those two extreme cases. And in the next video, we'll look at the N securities case. So it's not just 2 stocks, but now it might be 4, it might be 20. Obviously, this is more realistic, and we can transfer all our results from the 2 security case to the N security case. I hope you enjoyed this video, and see you in the next one. Bye.